Okay, so the easiest these problems can be is if you're given the velocity vector. Okay, if you're given the velocity vector as a function of x, then you just use that chain rule. You know, it can be one line like this. So the easiest these chain rule problems can be is when you're given the velocity vector. But often you have to figure out the velocity vector based on a speed and information about the path. So you have to come up with the velocity vector from the speed and the path. Okay, so to do that, just remember that the velocity vector is equal to the speed in the direction tangent to the path. So like, for example, if you had an object moving through a path like this, at this point, and say it's going this direction along the path, at this point, the velocity is in this direction. At this point, the velocity is in this direction, okay? It's always tangent to that path. And so, okay, so before I say that, so what kind of mathematical object represents a direction if we're trying to figure out a vector? Like when we break up a vector into its magnitude and its direction, the magnitude is a scalar. What represents the direction? The unit vector, right? So so we, for these, need to find a unit vector tangent to the path. Okay, so how do we do that? Well, the path is always given as a parametrization. Have any of you guys had that in calculus? That might be a Calc 3 thing. So like if you're parametrizing a curve, but the idea is that you're representing the position of an object based on a parameter. You're varying one parameter. So like if an object's going through a path like this, right, some crazy path, how many, okay, so this path requires 3 dimensions in general to live in, right? But how many dimensions is the path itself? It's not even 2, it's only 1, because, and the way to recognize that is at any location you can only go this way or that way. You only have one choice about where to go, you know? And so any one-dimensional object, like a path, you can represent with a single variable, okay? that variable is your parameter, and it can be a lot of things. It can be the arc length of the path, it can be time, it can be one of the position variables, but you can always represent a path using a single parameter. So a parameterization is a position vector where all components are functions of a single variable. Okay, so here are some examples. If you're given if your path is given in the form of a function like y is equal to x squared, okay, the parameterization of that is, well, our parameter, our one variable that we're going to represent this is going to be x. How do you represent the x component in terms of x? X, yeah. How do you represent the y component? X squared. So that's a parameterization that represents this function. Okay. It doesn't have to be, it doesn't have to be a position component that you parameterize by. It could be some arbitrary value, but as long as your parameterization depends on one variable, all of this stuff is true, okay? So once you have your position vector parameterized, you can find a vector that's tangent to the path by differentiating with respect to the parameter. For example, 1, if your position vector is x squared, then your parameter is x. So d dx of x gives you an x component of this tangent vector, and d dx of x squared gives you the y component. And so you get 1, 2x, and that's tangent to the path at x. There might be, but I don't remember it. Yeah, just call it that, a tangent vector.
And that would basically give you the velocity direction.
Yes, so that gives you a vector that's not necessarily a unit vector, but it is in the direction of the velocity vector. So once we normalize this, that gives us the unit vector that we're looking for to come up with the velocity vector. One other thing to consider with this is, so at a single point on this curve, like say here, how many vectors are tangent to that curve? There's actually 2, one this way and one this way. Yeah, so which one do we want? Well, you just need to know that doing this gives you a vector that's tangent to the path in the direction of the increasing parameter. Okay, so this gives us a vector that's tangent to the curve in the direction of x increasing. Okay. You could also, as a second example, you could have a position vector that is s squared 2s. And what is s? It doesn't even matter. It could be the arc length of the path, or it could just be some arbitrary parameter that you use to define this path. But if you want to come up with a vector that's tangent to that path, you take dds of each component, and you get 2s2, and this is a vector that's tangent to the path at s in the direction of increasing s. Once you have that tangent vector, just normalize it, get the unit vector for it. And that gives you the unit vector in the direction of the velocity vector. And then, so that's the unit vector. I'll call that u hat. And then the velocity vector is equal to the speed, capital V, times u hat. After what? Gives. U hat is the unit vector in the direction of V. Yep.
So what does that exactly mean? That's the direction of the increasing parameter?
Okay, so when you parameterize something, no matter what the parameter is, so like let's look at this crazy function. You go from point to point by changing the value of that parameter. Okay?
Well, I get that point. I'm just trying to figure out, you said.
Yeah, so I'm trying to get to that. So so if you change the value of the parameter, whether it's x or s or whatever, it moves you along this graph. So if increasing the parameter takes you this way, then that's the direction of increasing the increasing parameter. If increasing it takes you this way, then that's the direction of the increasing parameter. In a simpler case where your parameter is x, like say this is a case where everything is written in terms of your parameter x, then these are all tangents in the direction of increasing x. The opposite would be tangent vectors in the direction of decreasing x. They're just pointing towards bigger x values, but they're tangent to the curve. Okay, let's do an example. So let's say that an object moves along the path y equals sine of x, in the direction of decreasing x. And let's say that the speed is equal to 10 meters per second. What's the acceleration vector as a function of x? And B, what's the acceleration vector when x is at 1 meter? Okay, so what's happening here is an object's moving along this path. And is it moving towards the left or the right along this path? It's moving toward the left because we're talking about decreasing x. And so the unit vectors that we want in all these cases are the ones going this way. Our velocity vector, so remember where we're going with this problem is the acceleration vector is equal to the derivative of the velocity vector with respect to x times the x component of the velocity. So we need the velocity vector for both of these two pieces. And we are going to, so in some problems, you're just given the velocity as a function of x. In this problem, we're not given that, but we're given the speed, and we're given a path that we can use to find a unit vector. So we're going to figure out v, the velocity vector, as the speed times a unit vector. The speed is easy. That's just a constant value of 10. What about that unit vector? Well, our position vector is equal to x sine of x. And so a tangent vector in the direction of increasing x is derivative of the position with respect to x, so 1 cosine of x. So is that in the direction of our velocity at x? No, but negative of this is. So our u vector that's in the right direction is equal to negative 1 negative cosine of x because this particle is moving in the direction of decreasing x. Okay, so now we need to make this a unit vector. How do we do that? Yeah, so calculate the magnitude of this. That's, 1 squared plus cosine squared square root. So the unit vector is -1 over 1 plus cosine squared x square root, and negative cosine x over 1 plus cosine squared x square root. Okay? So that's a unit vector in the direction we want, and therefore the velocity vector is equal to, v times u, which is -10 over 1 plus cosine squared x square root, -10 cosine x over 1 plus cosine squared x square root. Okay, so that's the velocity vector as a function of x. And it's hard to come up with a problem where it's not a total mess. It gets messy because of that square root in the denominator.
How did you go from the absolute value of the u vector to the unit vector?
This is the magnitude, and so divide the direction vector by the magnitude, and it gives you the unit vector. Okay, so now we're ready for the chain rule. We know that the acceleration is equal to derivative of the velocity vector with respect to x times the x component. It's really hard to imagine that I'm going to go through all this right now. But, that derivative is going to be really ugly. But take that derivative, multiply it by the x component of the velocity, and you get the acceleration. Oh, you know what? Let's do one. Okay, let me do another one. Okay, that derivative is ugly. Let me do one where the answers will come out nice. I mean, you can all do that, but it'll take you all a long time, and it'll take me a long time. So let's do an example where it's not going to come out too messy. So let's say that this one is pretty similar to one of the practice problems, I think. So let's say that an object moves around a helix where the position vector is defined by cosine of z, sine of z, z. And the speed is constant at 5 meters per second. What's the acceleration vector as a function of z? No. That's not going to work either. That's going to be a mess too. Okay, let's not do that.
No, that if you hit that problem, it actually does work out pretty easily.
Does it? But you still have that z there. That keeps
No,
it from.
goes away when you take the derivative. You did it really messy in your solution. It ends up being a real easy denominator, like the square root. Because the square root of cosine plus the square root of
Yeah.
square sine.
But I just wanted it to be the square root of cosine squared plus sine squared and just be 1. And then it's already a unit vector.
all our calculators can do that. But no, if you have, undo that once. Because the third component of your magnitude is going to be 1.
Right.
It would be cosine squared plus sine squared.
Oh, so square root of 2.
Square root of 2. It's really simple.
Oh, yeah. All right, let's do this. All right. Yeah. So we need the, okay, and let's say it's in the direction of increasing x. Let's do this problem.
Well, wouldn't you have to be
Increasing z, yeah. Sorry. Okay, so the vector in that direction is negative sine of z, cosine of z, 1. And that's not quite a unit vector, but to get a unit vector, the magnitude is sine squared plus cosine squared plus 1 square root. Sine squared plus cosine squared is 1, so this is square root of 2. And so the unit vector is negative sine of z over root 2, positive cosine of z over root 2, and 1 over root 2. And that means that the velocity vector is 5 meters per second times this. So negative 5 over root 2 times sine of z, positive 5 over root 2 times cosine of z, and positive 5 over root 2. So now we have a fairly nice looking expression for the velocity vector. So the acceleration vector is dv dz times the z component of the velocity. So that is, so the derivatives here are, so negative 5 halves cosine, negative 5, not, so negative 5 over root 2 cosine of z, negative 5 over root 2 times sine of z, 0, times the z component of the velocity, which is 5 over root 2, and so you get negative 12.5 cosine of z, negative 12.5 sine of z, and 0. Any questions about that? Yeah, I went on for like pages in my solution, right?
It was terrible.
Yeah, well, this is a better way.
What's the purpose behind the magnitude? Like, why is that step factor in there? What does that do?
That's to get the unit vector. So if you have, and that stuff, there's a little refresher on all that stuff if you look at the vector review that's posted. But if you have a vector, so like, what's a unit vector in the direction of 10 minus 3, 1? The magnitude of this is 10 squared plus 3 squared plus 1 squared square root. And so a unit vector in that direction is 10 over root 110, negative 3 over root 110, and 1 over root 110. So that's all I'm doing is just calculating that unit vector. Any other questions about these?
Is the VZ just always going to be positive, or will you also be negative there in your acceleration?
The VZ.
Right, with your 5 with 2.
Uh-huh. This one over here.
Oh, yeah.
This is
I
a
gotta go
speed.
back to what it was originally.
Okay, this is a speed, so it's always going to be positive.
Okay.
So how about this? So say that there is a hill that you're going to approximate as the function y equals x squared in meters. That probably is a pretty steep hill out here. And a skier skis in the direction of decreasing x. What's the acceleration if the skier starts at position x equals 20? Okay, so this is an example to kind of show, to motivate like where a lot of these kind of problems might come from. Based on physics 1, how would we solve this problem? I don't know, I wasn't listening. Well, this is the kind of thing, like a lot of times this is sort of an example problem for conservation of energy, right? So so you'd say mgh plus 1/2 mv squared, and initially that's 0, is equal to what are we trying to find here? We're trying to find speed as a function of height. So this would be 20 squared, so 400. Mgh, and that height is going to be x squared because of the path, plus 1/2 mv squared. Okay, so we can use something like this to get a function, to get the speed as a function of x. We can divide out all the m's, and we get 400 g minus gx squared is equal to 1/2 v squared. So v is equal to 800g minus 2gx squared square root. Okay, so now we have a path defined by this, and we have a speed defined by this. Both of those are in terms of the parameter x. And so now you can go through those steps that we've been going through to come up with the acceleration as a function of x. This would be a horrible mess like the other ones, but so you'd go, the velocity vector is equal to v times u, and the acceleration vector is dv dx times the x component of the velocity. Any other questions I can answer about just sort of this overall approach or any of these example? Yep.
That would just be the maximum velocity.
This here, this is the speed. So we'd still need to use the path to come up with that unit vector, and then multiply this expression for the speed to it. Any other questions? Okay. So test 1 tomorrow is just on differential equations, and then the test next week will be on this stuff and kinetics, and maybe more.